All right, so in Chapter 7, we're going to be discussing how energy is associated with chemical reactions and how we can measure that energy, how fast these chemical reactions could go based on the energy, and then also what equilibrium is. So there's kind of three major concepts in there. The main one we're going to focus on in Chapter 7 is energy. Okay, rate and equilibrium, we're just going to kind of hit a few concepts of it, and that's it. Okay. Okay, so first off, let's define thermodynamics, and that is the study of energy. And this thermodynamics is going to be applied to chemical change that's occurring. So as a chemical reaction is proceeding forward, there will be either heat lost or gained, okay, due to that the change that's occurring. All right. So the concepts from we talked about the kinetic molecular theory in Chapter 5 with gases, how these molecules and atoms in a reaction mixture are in constant random motion. Okay, that was true for gases as well, but it's true if they're in a solution. Molecules and atoms frequently collide with each other. Only some collisions will allow the reaction to proceed because the bonds will break. Okay, so if the bonds break because of the collision, if there's enough energy in the collision, they will break, and then the reaction will proceed. Otherwise, they just bounce off of each other and they go on their way. Okay. When reactant bonds are broken, new bonds may be formed and products will result. Okay, so that's kind of the idea behind what's happening. We have these collisions. As they collide, they absorb energy, and the absorption of energy allows the bonds to break. And if the bonds break, then we can create new products. If they just collide and bounce off of each other, then obviously there's no reaction. And that's going to affect the rate of these reactions as well. Okay, now when we're talking about thermodynamics and heat energy lost or gained, we have to define two systems. The first of those two systems is the thing that's under study, the process under study, and we're going to refer to it as the system. Okay? What we are studying, that's our system. The surroundings is what's around it. And here we can say the surroundings obviously is the entire universe. But more specifically, if you're carrying out a chemical reaction, you can isolate that reaction from the rest of the universe and create your own little space inside of a reaction vessel. Okay? So if I have a cup and I carry out a chemical reaction inside of it in a water solution, then the reaction is the system. The surroundings will be the water that's surrounding the thing under study. Okay? So the water can change temperature based on what the system is doing. Okay? So here we can see, here's a system, here's its surroundings. If the system releases energy, what's going to happen to the temperature of the surroundings? The temperature of the surroundings will increase as the system is losing energy. Okay? So if the system loses, we say that's exo. Well, how would I describe the temperature of the system then? Is it increasing or decreasing? If energy is going out of it and causing this to increase, then the system energy is what? Decreasing. The temperature of the system would be decreasing, whereas the temperature of the surroundings would be increasing by the exact same amount. Okay? So if this decreased by 5 joules of energy, this would increase by 5 joules of energy. Okay? And vice versa. If the surroundings gains energy, so heat energy is going into the system, what's going to happen to the temperature of the surroundings? It's going to decrease. The temperature of the system is increasing. The energy of that system is increasing. Okay? So this energy is going up this energy is going down by the exact same amount. So 5 kilojoules absorbed, okay, by the system is 5 kilojoules lost by the surroundings. How would this feel to the touch? Hot. How would this feel to the touch? If energy is being drawn out of it, how would it feel if I touched it? Would it get hot? Well, this one's getting hot, so this one's what? It's getting cold. So if I carry out a chemical reaction and it feels cold, then what's happening? Energy is being what? Absorbed from the surroundings into the system. Okay? We say that that is endothermic. If energy is being released, we say it's exothermic. So if my chemical reaction feels hot, that means energy has been released from the chemical reaction. And it causes the surroundings to feel hot. If the chemical reaction feels cold, it's causing the surroundings to feel cold because it's absorbing energy. Okay? It's absorbing energy into it. So we would say that this energy going this way for the surroundings, okay, that's a negative 5 kilojoules, and over here it's a positive 5 kilojoules increase. Here would be the 5 kilojoules, negative 5 kilojoules would cause a positive 5 kilojoules increase. So it's exactly the opposite, right? This is being released, this is being absorbed. Here it's being absorbed, and so this is it's being released from the surroundings and absorbed by the system. Okay? So the sign is opposite between the system and the surroundings. This is an important concept that we need to try to understand. The system and the surrounding have opposite signs. Okay? So, the first law of thermodynamics is that energy in the universe is conserved. That's where this whole concept of if you lose 5, I gain 5 comes from. Okay? We don't create energy. We don't destroy it. It just gets transferred around. Right? So, if our plants absorb energy from the sun, that energy wasn't created by the sun. It was released by the chemical reactions occurring in the sun. Okay? It was always there. It just had to be released. Okay? So that's the first law of thermodynamics. Also called the conservation of energy. Okay? So we can follow that energy, basically. So here we have a reaction A plus B, AB plus CD forms AD plus CB. Okay? What had to happen? I had to break this bond and this bond, right? And then the molecules were able to rearrange themselves. Well, breaking bonds requires what? Energy. I have to absorb energy. So this is a plus amount of energy. To absorb energy, it's an increase in the energy. What do you think happens then when I make bonds? If breaking bonds absorbs energy, what happens when I make bonds? Energy is released. Okay? So I'm getting energy out when I form these bonds. Here I have to absorb energy to break them. Okay? That's how chemical reactions work. Before the chemical reaction can actually take place, those molecules have to collide with enough energy to break the bonds. If they do, then they will react and form new bonds that will release energy. Okay? And we can measure how much energy is absorbed or released in these chemical reactions. So these bonds must be broken. These bonds are formed releasing energy. They will release energy. Okay? So this is the endothermic part of a reaction, and this is a exothermic part of a reaction. Every reaction has an endothermic and an exothermic part to it. They all do. Okay? But the question is, which one's greater? Did I absorb more energy or did I release more energy? That's how we describe the reaction. If I released more energy than I absorbed, then this reaction is considered exothermic because it releases more energy. If I absorb more energy than I released, then this reaction would be endothermic because it requires more energy than it will release in the end. Okay? So the net effect is what we're looking at. Does it feel hot or does it feel cold? If it feels cold, that means I absorbed more energy than I released. And so then, therefore, this is an endothermic reaction. If it feels hot, I released more energy than I absorbed. So therefore, this is an exothermic reaction. Okay? So endothermic reaction requires, the energy required to break the bonds is greater than the energy released. Okay? Okay, so here we see a couple of reactions taking place. Okay, and here's our energy difference. Okay? So here I have a combustion reaction. And look how I write it. Okay? CH4 plus O2 produces carbon dioxide, water, and 211 kilocalories of energy. This is written as a product of the reaction. If energy is a product, that means energy is being released. So this is an exothermic reaction. If I write the energy as a reactant, though, look, 22 kilocalories plus NH3, that decomposes it into N2 and H2. So if I write it as a reactant, therefore it is an endothermic reaction. It requires this much energy to cause the decomposition of NH3. Okay, so we describe it as an endothermic reaction because it's absorbing energy. Does that mean it didn't release any energy at all? No, it did. It's just that the net effect is that we absorbed more energy than we released. Maybe we absorbed 24 kilocalories of energy and we released 2 kilocalories of energy. Okay, now do you see why it's 22 kilocalories? Because 2 calories cancel from each side. And now I'm left with 22. Okay, so it's the net effect that we care about. That's how we'll describe these reactions. Okay, so enthalpy of a reaction is simply the energy per mole. How much energy is there per mole of a reactant? That's what the enthalpy is describing. And energy is described as the unit Q. Okay? And so Q per mole is what we call the enthalpy change, the change in the energy. The products minus the reactants. Okay? So like I said, if we had 23 kilocalories of energy released from the products, we would have, and we had 6 kilocalories of energy absorbed from the reactants. Okay, then we can easily see what our overall net effect would be. Okay, so we're going to have 6 of these are going to cancel for 6 of those. And we're going to be left with a net effect of the energy. You don't actually have to calculate these. Okay, that's not something we're going to do in here. Okay, but that's the idea. Products minus the reactants. We're looking at the overall effect. What is the overall effect that we're getting from this? Okay. Now, this is something, though, that you do need to be familiar with, is the sign of delta H. If delta H is negative, then that is an exothermic reaction. Negative 211 kilocalories of energy. That means this is a exothermic reaction. Here, we didn't write it as negative 211 kilocalories. We just wrote it as a product, and we said it was exothermic. But my delta H here would be equal to negative 211 kilocalories because this is an exothermic reaction. Here, my delta H equals a positive 22 kilocalories of energy because it's an endothermic reaction. So the sign of delta H tells me what type of reaction it is, or it tells me where I should write the energy in the equation as either a product, negative as a product, or as a reactant, okay? Because it's a positive delta H. So that's where we got this positive 22 kilocalories for the endothermic decomposition of NH3. Okay? Okay. Are the following processes exothermic or endothermic? So, fuel oil is burned in a furnace. Okay? It's exothermic. How do I know? It releases heat. That's exactly why. That's how I know. It's getting hotter. It's releasing energy. So if it's releasing energy, it's exothermic. Okay? How about this one? Endothermic, exothermic. Look at the delta H. That's what's going to tell you in this one. Delta H is negative or positive? Negative. What does that mean? Exothermic. Okay, look at the last one. Energy is a product of this reaction. Endothermic or exothermic? Exothermic, because it's a product of this reaction. Okay, so all three of these are exothermic reactions. Okay, written basically in three different ways. Okay. Okay, so spontaneous and non-spontaneous reactions. So exothermic reactions are usually spontaneous. So if you release energy, then that's usually based on the fact that it's a spontaneous process, meaning the reaction actually happens at that temperature. Okay? So it's a spontaneous reaction. Endothermic reactions, for the most part, are non-spontaneous, meaning you have to add energy to them to get them to go to actually occur. Okay? You have to keep feeding it energy in order for that non-spontaneous process to occur. Spontaneous processes occur without the additive energy. Okay? They just occur spontaneously on their own without any extra help. Okay? So endothermic processes are usually non-spontaneous. But are they always non-spontaneous? No. They're not. Are all exothermic reactions spontaneous? No. They're not. Just most. Okay? So there are those exceptions out there. So that means, if that's true, then we can't describe spontaneity based on whether you are exothermic or endothermic. So therefore, spontaneity must be based on whether you are exothermic or endothermic and something else. And the other factor is this, entropy. Okay? So whether you are a spontaneous reaction will depend on whether you have the right kind of entropy and enthalpy, which is endothermic, exothermic. So enthalpy means endothermic, exothermic. Entropy means how much disorder there is. Okay? The universe spontaneously tends towards randomness and disorder. This is a physical law. Okay? So it's the second law of thermodynamics. that basically everything just falls apart. It's a law of physics, okay? You can see it happening. I'm sure if I go into your bedrooms in your apartments, we can maybe see that process happening, okay? I can guarantee it if I walk in my kids' bedrooms. I see it all the time, okay? The entropy in there is just ridiculous sometimes, okay? So, but that's a spontaneous process. It doesn't require you to do anything for chaos and disorder to occur around you. What requires energy is for you to organize things and keep them organized, right? That's the non-spontaneous thing. So things tend to want to just fall apart. And to keep them together, you have to have an input of energy. So if I couple an increase of the disorder, which is spontaneous, that's the spontaneous process, with exothermic reaction, that's going to be a spontaneous process, okay? Or if I couple an ordered process with an endothermic reaction, that's always going to be non-spontaneous. But what happens when you couple an endothermic process with with something that disorders itself? So that seems kind of backwards. Or an exothermic process with something that becomes more orderly. So when those two odd situations occur, that's when we have to consider something else, which is the temperature at which you carry out the reaction. Okay? So there will be a division with those two situations I just mentioned. There will be a division where it will go between spontaneous and non-spontaneous. Okay? So let's look at this and decide about entropy really quick. Helium gas or sodium solid? Which has greater entropy, meaning which one is more disordered and unorganized? A gas or a solid? The gas. This one has the greatest entropy. Okay? Liquid, water, or or gas vapor. Which one is more disordered? The liquid or the gas? The gas. The gas has the greatest entropy because it is the most disorderly. Okay? So, the entropy can also be determined by simply taking the entropy of the products minus the entropy of the reactants and find the change in the entropy. Okay? You don't have to calculate that, but that's how it's discovered. That's how you determine it. So a positive delta S, what does that mean? If the entropy is increasing, what does that mean about the disorder? Is it decreasing or increasing? An increase in entropy means what? Greater disorder. Greater disorder. A decrease in the entropy means less disorder. It's more organized. Okay? So when we're thinking about entropy, that's how the signs of the entropy are going to help us understand what's happening. Whether it's becoming more or less orderly, the system. Okay? Here we have some phase changes. Can't see it very well. Okay? So we're going from a solid to a liquid. So it's melting. Is that an increase or decrease in the entropy? Delta S is positive because it's becoming more disordered. Okay? Now from the liquid to the vapor, delta S is positive as well because Look, it's becoming more disordered, right? So it's still positive. What about the solute here? Nice little organized salt. What happens to it? It gets broken apart. So we would say that delta S there is also positive. Okay? So we have positive delta S's for all three of those situations. Okay? So all these have a positive delta S. Okay, so if it's exothermic and positive delta S, then that will always be spontaneous because we're releasing energy and it's becoming more disorganized. Those two things go hand in hand. They're both those are the most spontaneous things. Disorder is spontaneous. Releasing energy is spontaneous. So you couple those two things together and you get a spontaneous process. If you decrease temperature and your system becomes more organized, both of those situations decrease in the, so an endothermic reaction, in other words, an endothermic reaction and a negative delta S, you couple those, the process is always non-spontaneous. It's always a non-spontaneous process. Okay? For any other situation where you would have endothermic and a positive delta S, meaning endothermic, I'm absorbing energy and I'm becoming more disorganized. Okay? Or exothermic, where I'm releasing energy and I'm becoming more organized. Okay? For those two last situations, then it is dependent on the relative size of delta H and delta S and the temperature. Okay? So let's look here. We have this flask. If I open the valve in the middle here, this gas will spontaneously do this, right? It'll fill the other side. Well, what if I started here? Can I go backwards? Is it going to spontaneously do that? It won't, right? That's going to require energy to do that. So that's an example of how these delta S spontaneously tend towards more disorder, but not the other way around. It's not going to spontaneously go backwards. Okay? Okay, now, so how do we know if a reaction is actually going to be spontaneous or not? Well, it's calculated through this delta G, which is the free energy of the system. Okay? Delta G equals delta H minus T delta S. So you see here the temperature dependence when I have delta H and delta S reactions here. Okay? So this is what you need to know about this. You don't actually have to calculate delta G. This is how you need to understand. If the signs are opposite, then delta G will have the same sign as delta H. Delta H positive, delta S negative, delta G is positive. Delta H negative, delta S positive, delta G is negative. Always. What does delta G positive mean? Delta G positive means non-spontaneous. This is the non-spontaneous situation. Delta G negative means spontaneous. This is a spontaneous reaction. Signs are the same. Delta H positive, delta S positive. Depends on temperature. Delta H negative, delta S negative. Depends on temperature. That's about it. That's about it. That's all you have to know for those. Okay? So as far as entropy and enthalpy go, you need to understand how to identify an endothermic and exothermic reaction, meaning is energy being released or absorbed. You need to know how to identify whether the entropy, meaning the disorder, is increasing or decreasing. Okay? Whether it is going from gas to liquid, it's decreasing, or From a solid to gases, it's increasing. Okay? And then be able to predict the sign of delta G based on the signs of delta H and delta S. If the signs are the same, then you simply need to tell me that it's temperature dependent. Okay? You will not actually have to calculate where it is that it changes from spontaneous to non-spontaneous. At what temperature is delta G equal to 0? That's where it's both spontaneous and non-spontaneous. That's the equilibrium temperature, where delta G is 0. Okay. Now we're going to talk about calorimetry. Some of you were already exposed to calorimetry last week in the lab. Okay, but calorimetry is simply the process of measuring the energy associated with a chemical reaction using a calorimeter or a calorimeter and a thermometer. Okay, so you take your calorimeter, and which is, a lot of times just a coffee cup or something that's insulated, something that's insulated. That's what you need. So if I have an insulated container, then I can carry out a chemical reaction inside of it without losing a lot of the energy to the surrounding universe. Okay, it's contained in that container, and so that's why we carry it out in this insulated cup, and we measure the temperature change just simply using a thermometer. Okay. Now, as you can see here, this is a reaction mixture. That means whatever's inside of the water is what's reacting. The water isn't reacting. The water is the surroundings. The reaction is taking place inside of the water. So if my temperature of the water is increasing, what does that mean about the temperature or the energy of the system that's under study? Is it endothermic or exothermic? Why is the water temperature rising?
The system is releasing.
Exactly. The system is releasing energy. So if the system's releasing energy, the temperature of the water will rise. What type of reaction is that? Endothermic or exothermic? Exothermic. The water feels what? Hot or cold? The temperature is increasing, it's going to feel hot. Okay? So that is because the water is absorbing energy. The water will absorb the energy. That's an endothermic process, but it's the system that's releasing it. Okay? So as the system releases the energy, the water absorbs it and increases temperature. But we don't describe it as an endothermic reaction. We describe it as an exothermic reaction because we're not studying the water. We're studying the system inside of the water. Okay? So if I have a positive temperature change, that's going to give me a positive answer. But how do we write the delta H of an exothermic reaction? As a positive or a negative? What's this doing? Delta H positive, delta H negative. Exothermic, delta H negative is exothermic. But I have a positive temperature change. That's going to give me a positive delta H. Well, we simply change the sign because we just calculated the delta H of the water, but we want it to be the delta H of what? Not the water, of the system. So we change the sign. And we say the system released this much amount of energy. The water absorbed this amount of energy. Okay? So when we're doing these reactions in our calorimeter, okay, we simply change the sign so that the change in the energy is associated with the system, not the surroundings. Okay? So that's where Q comes into play. Q is the energy calculated for the system, okay, based on the temperature change of the surroundings, which is the water, in most cases. Okay? So here is an equation that we would use to calculate Q, which is the energy in joules or in calories. Okay? So Q equals the mass of your solution times the change in the temperature times your specific heat. So specific heat is a constant. It doesn't change. And it's related to the substance that you're carrying the chemical reaction in. So if it's a water solution, then the specific heat of water for water is 4.184 joules per gram times degrees Celsius. Okay? That is the specific heat of water. So if this reaction is being carried out in something else like ethanol, then I can't use 4.184. I have to use the specific heat of ethanol, not of water. Okay? So it's important that you know what the surroundings of your system is so that you can use the correct specific heat of that surroundings. Okay? So, here we go. Here's an example. If 0.1 moles of HCl is mixed with 0.1 moles of potassium hydroxide in a coffee cup, the temperature of 150 grams of solution increases from 25 degrees Celsius to 29.4 degrees Celsius. If the specific heat of the solution is 1 calorie per gram times degrees Celsius, calculate the quantity of energy evolved in the reaction. Do you see how they told us what the specific heat was? They're going to tell you what it is. It's not something you're going to calculate. Well, I guess potentially you could calculate it. But it's something that's already been determined most of the time, and they'll give it to you either in a chart or in the question they'll say this is the specific heat. Okay? So then I use this equation. Q equals the mass of the solution times the change in the temperature of the solution times the specific heat of the solvent in this case. So here my mass is 150 grams times my change in temperature. It is 4.4 degrees Celsius. Well, I had 29.4 as my T final, and my initial temperature was 25.0 degrees Celsius. Okay? And so that allows me to end up with 4.4 degrees Celsius temperature change. Okay? So this is a 4.4 degrees Celsius temperature change. It increased temperature, right? So temperature changes are always calculated by final minus initial. So this is a positive temperature change. It's increasing. If it decreased in temperature, that would be a negative temperature change. So for example, if I had started at 29.4 and went to 25, I would reverse these, and then I would say 25 minus 29.4, and I would get a negative 4.4 degrees Celsius. Okay? So, and then I would have used the negative here as my 4.4 if it was a decrease in the temperature. And that would give me a negative Q. But in this case, because it increased temperature, I get a positive Q. 6.6 times 10 to the second calories, or 660 calories of energy was required. So specific heat, okay, if we define what the specific heat is, here we're told that the specific heat is 1 calorie per gram times degrees Celsius. Or in other words, the specific heat is the amount of energy required, 1 calorie, to change 1 gram of a substance by 1 degree Celsius. Okay? So for water, we said water is also 4.184 joules per gram times degree Celsius. So in other words, it takes or requires 4.184 joules of energy to change the temperature of water, 1 gram of water, by 1 degree Celsius. Okay? That's what this is telling me. And because I have that, if I plug it into this equation, if I know the mass of the substance, and I know the temperature change, and I know the specific heat, I can be able to calculate just the energy that was required to carry that out. How much energy was required? Okay? And so that's why the specific heat is so valuable to me. If I know it, I can figure out the energy. Okay? Okay. Is the reaction endothermic or exothermic? Okay. Now, it's a little misleading because the sign of the Q is not negative. Negative would be exothermic. The sign of Q here is positive. But this is an exothermic reaction. Why is it an exothermic reaction? Because the system released the energy to the water, which changed temperature. Okay? So that's why Q here is positive. So if I wanted to describe this as the Q of the system, I would simply make it a negative. Negative 6.6 times 10 to the second calories of energy was released from the system to the surroundings and absorbed by the surroundings. So that's why the surroundings is positive. Okay? During this reaction. Go away. Okay. So this reaction is exothermic because the energy was released from the system to the surroundings. What would be the energy evolved for each mole of HCl reacted? So 0.1 moles of HCl used in the original reaction. So if I wanted to know how much energy per mole, which is your delta H, okay? So delta H would be equal to the calories per mole, okay, in this case. So the delta H of this reaction would be 660 divided by 0.1 moles, because that's the amount of HCl. That's how many moles of HCl were reacted. Okay, so we simply say the energy per mole, and then that'll tell us. Okay, a bomb calorimeter. So this is how they measure energy in your food. They take some food. They put it in the little bomb here. This is a bomb. And this is water surrounding it. Okay? So they know the mass of the water that's in here. And they take a sample of the food and they burn it. Okay? And as it burns, it releases energy to the water. So the energy is exiting the bomb, this thing in the middle here, and it's going out into the water. And the water is going to change temperature. Okay? So they can measure how much energy is in that sample of food because of how much energy is transferred to the water when they burn it. So this is how they measure they would do fuel value of food. Okay? But of course, 1 kilocalorie of energy is equivalent to 1,000 calories. But when we're talking about food, we don't see energy written in calories with a little c. We see energy written with calories with a big C. Well, a big C calorie is equal to 1 kilocalorie, right? So we've talked about this, right, before? Yeah? So if it's 250 calories in your candy bar, that's 250,000 calories in your candy bar. Okay? And that's what they mean by that. Okay, so 1 gram of glucose was burned in a bomb calorimeter. 1,250 grams of water was warmed from 24.5 degrees Celsius to 31.5 degrees Celsius. So we have a delta T. 31.5 minus 24.5 would be our change in temperature. We have the mass of the water, which is 1,250 grams of water. Okay? And we have the specific heat of water. So we can calculate the energy of the water. So here, 6.1 degrees Celsius temperature change. Okay? So we can calculate the mass of the water times the temperature change times the specific heat in calories. Sometimes your specific heat is given in calories or joules. If it's given in joules, your answer will be in joules. If it's given in calories, your answer will be in calories. So here I have 7,600 calories of energy. Okay? But they don't want to write that on the label, so they say 7.6 big C calories. They say 7.6 calories, okay, of energy instead of 7.6 kilocalories, which is what it would be. Okay, so we'll do a few practice problems on that next time, okay, on calculating the energy associated with chemical reactions, okay. So now we're going to move into kinetics. So kinetics is a study of the rate or speed of chemical reactions. How fast does your chemical reaction go? Okay. So some reactions go really fast. Some reactions are very slow, like rust. Rust doesn't just happen immediately, right? That's a fairly slow process. So there's a kinetic measurement associated with that. So here you can see that as molecule A disappears, which is a reactant, molecule B is appearing, which is a product, at the exact same rate. Because this appearing is dependent on this disappearing. So they're going to disappear and appear at the same rate. Okay? That's how chemical reactions work, right? Especially if your coefficients are 1 and 1. Then the rate of your disappearance will be the same as the rate of the appearance of the product. Exactly the same. But if your coefficients are, say, 1 and 2, then that's different. Because one molecule produces 2 over here. One of these produces 2 over here, so the rate of disappearance of one of these causes the other thing to appear twice as fast, right? So your coefficients also are important in these rates. So here we can see red is disappearing, white is appearing, okay, over time, simply based on the fact that white is the product, red is the reactant, and as red disappears, you'll get more and more A, and eventually you'll run out of red, and you'll be left with just white. So one way that we can measure rate of reactions, a good way, is through color changes. So these color changes can be associated with the concentration of something in the reaction. So let's say that this is the most concentrated solution. So there's a reactant in here that is brown. And right here, it's fairly concentrated. A few minutes later, it looks like this. A few minutes later, it looks like this. And a few minutes later, it's clear. So we can measure the concentration over time based on the color changes here. Especially if we use a spectrophotometer that can measure the concentration based on how deep the color is. Okay? And so we'd be able to create a rate. A rate is the molarity of your reactant over time. How fast does your reactant disappear over time? The change in the molarity of the reactant over the change in time. That's how I calculate a rate. Okay, so here we have a reaction. Methane plus oxygen produces carbon dioxide, water, and 211 kilocalories of energy. Is this endothermic, exothermic? Exothermic, because energy is a product of this reaction. Delta H would equal negative 211 kilocalories of energy. Okay, so this is an exothermic reaction. CH and OO bonds must be broken, right? They have to break, and the CO and OH bonds must be formed over here. Okay, energy is required to break the bonds. So the energy, where does it come from to break those bonds? It comes from effective collisions. So if I want to increase the rate of a reaction, if I want it to go faster, then I have to increase the effective collisions. I have to increase how many collisions are occurring in a specified amount of time, but not only that, how effective they are. Because you might have a molecule that comes and hits, maybe it would have had enough energy if it had collided in the correct way, but if it collides like this, it won't do it. If it collides like this, that's the correct orientation, the correct way, it's going to react, and it's going to go forward. That's what we mean by an effective collision. That it has all the correct parameters for that reaction to take place. But if something's off kilter or out of whack, it's not going to happen. It's just going to bounce off and it's going to go on its way. Okay? So to increase the rate, we want more collisions, and we want them to be effective collisions. The more effective collisions we have, the faster the reaction will take place. So the energy required to break the bonds of a reaction, we call that the activation energy. Meaning the energy that's going to be required for that reaction to actually happen. So if there's not enough energy in the collision, the bonds will not break and the reaction will not proceed forward. But if there is enough energy in the collision, the bonds will break and the reaction will occur. So we have to have the right amount of energy. That's the activation energy. So if we can overcome that barrier of the activation energy, the reaction will occur. Okay, and we call it an activated complex. This is how we show that in a diagram. Okay, so right here, this is the amount of energy required excuse me, for the reaction to take place. That's the activation energy. Okay, this is the activation energy. If I overcome that amount of energy, my reaction will proceed forward. Okay, so this is the amount of energy absorbed, and this is the amount of energy released. So how would you describe this reaction? Endothermic or exothermic? Exothermic, because it releases more energy than it absorbed, right? This amount of energy is canceled out. This is the amount of energy that's left. And it was released. Okay? So this is an exothermic reaction. And it has a net release of energy. And the activation energy was lower than the amount of energy released. So what kind of reaction is this? This is how much energy is absorbed. This is how much energy is released. This is endothermic. it requires me to absorb this much energy, and it only releases that much. So the overall effect is that this amount of energy right here is the amount of energy absorbed, and this energy cancels. Okay, that's the net effect. So I have a greater amount of energy absorbed than released. This is endothermic. This is an endothermic reaction. Okay? The activation energy is much higher on endothermic reactions. And they will release just a little bit amount of energy. Okay? That's how they're going to work. Okay, so what affects the rate of a reaction? Well, things like the structure of the reacting species. Are they really big? Are they really small? Is there an opening where I need to collide? Okay, so all these things are going to take place based on the structure of these reactions. The shape and orientation. Okay, if I collide in one place, the reaction won't happen. If I collide in another, it will. So I have to be oriented correctly for this reaction to take place. Concentration. If you increase the concentration of a reactant, that will increase the rate of the reaction because there's just more stuff reacting. There's more collisions occurring. And so you're increasing the number of effective collisions, and so therefore increasing the rate. Temperature of a reactant. If you increase the temperature of the reaction, it's going to allow the rate to increase because you're adding energy to that system, allowing for higher number of collisions and more effective collisions. Physical states of reactants. Is it a solid? Is it a liquid? Is it a gas? Is it a solution? Okay, those will affect how fast the reaction is going to occur. Presence of a catalyst. A catalyst will cause the reaction to go faster, and we're going to talk about why. Why will that happen? Okay? So here we can see that if you have oppositely charged species, obviously they're not going to react. Okay? Never. They're never going to react because they're never going to be able to collide because those opposite charges will just push each other away. Ions of the same charges do not react. Bond strength plays a role. So if I have something that's like this versus something that is like this, okay, which one's going to have more reactions occurring? The nitrogen or the oxygen? Which one will break its bonds more easily? Oxygen will break its bonds more easily because it's a double bond. And the energy associated with breaking a double bond is less than the energy required to break a triple bond on the nitrogen. So if I burn methane gas or whatever it is on my Bunsen burner in the laboratory, okay, what do we say it reacts with? Do we say it reacts with nitrogen in the air? Nope, we say it reacts with oxygen in the air, right? And it's burning with the oxygen in the air. Why? Because the oxygen requires less energy to react with the gas. Because to burn the nitrogen, I would need a higher, more energetic reaction. So but there's much more nitrogen in the air. Way more nitrogen in the air than there is oxygen. But yet, I react it with the oxygen because the oxygen reacts more easily. Okay, so larger molecules may obstruct reactions. Only molecular collisions with correct orientation lead to product formation. Okay, so this is important. You can't have a chemical reaction occurring without the correct orientation. So this is where our bodies are great. Okay? They carry out chemical reactions all the time. But they do it in very effective ways because they orient molecules. they position them just correctly and perfectly so that those chemical reactions can occur almost instantaneously. Okay? And we'll talk a little bit more about that. Concentration of reactants, increase the concentration. You're going to increase the number of effective collisions. Okay? Higher concentrations mean more reactant molecules per unit volume. More reactant molecules means more collisions per unit time. Okay? Temperature. I'm adding energy. The particles are getting faster. There's a higher likelihood of effective collisions with enough energy to break those bonds. So higher kinetic energy means higher percentage of collisions. Solid state. So the solid state is a terrible way to carry out a chemical reaction if you want it to go fast. So if you have two solid things and you put them together, then they can only react on their surfaces. And so the number of effective collisions that's occurring is very reduced because they can only effectively touch each other where they're touching. Okay? Now, you could try to increase the surface area by making it into small, powdery stuff, and that would help. If you mix those together, that might help increase the surface area of the reactions. Okay? Still not the most effective way. So solid state is the least effective way to carry out a chemical reaction. The gas phase, more effective than the solid phase. But in the gas phase, the problem is the particles are still far apart. They're spread far apart from one another. And so the number of collisions is only effective when they're, or to increase the collisions, you can increase the temperature or maybe decrease the volume, and then you'll have more. Okay, so that's going to increase pressure and things. But still, you can never get them close enough so that they would match how effective it is to carry out reactions in the liquid phase or in aqueous solutions. Because in the liquid phase, everything's touching. And you're getting very fast reactions because there's a high percentage of effective collisions occurring, much more than in these phases. Okay? They're in close proximity and they're free to move. So reactions are faster in the liquid state and slowest in the solid state. So liquid phase is the best way to carry out a chemical reaction, or an aqueous solution is good. Okay, and finally we get to the catalyst. So what does a catalyst do? Well, a catalyst lowers the energy requirement. So do you see your activation energy here? Your catalyst causes that activation energy to be lowered so that the reaction doesn't require as much energy, so therefore you can have more effective collisions with less energy. Okay? And so how does a catalyst do that? Well, it does that by orienting molecules correctly. It holds them in place. It stresses bonds. It puts stress on bonds so that those bonds will break with less energy. So some of the best examples of catalysts are the ones that we find in our bodies, enzymes. Enzymes carry out chemical reactions in our bodies, in living things. They're proteins that carry out these chemical reactions. And they can do it so effectively that I mean, it's just unbelievable. If you take two nucleotides, let's say, so DNA is made of 4 nucleotides, right? Adenine, thymine, guanine, cytosine. You take those nucleotides, you put them into a test tube, you let that test tube sit for, I don't care, a year. You're not going to come back and have a strand of DNA. Okay? It's just not going to happen. Why? Because those things are ginormous, and they're just going around, and there's not enough energy for them. They might collide, but they're just ineffective collisions. But if you take polymerase, DNA polymerase, and you take a strand of DNA that acts as a template for orientation purposes, you position that nucleotide on that strand of DNA, and polymerase orients everything, stresses bonds, brings in the next nucleotide just in the correct, perfect position. Boom, it reacts, and you form that bond. Okay, that phosphate hydroxide bond that forms the backbone of the DNA, right? And it happens super fast, like so fast. It's unbelievable. Just have to show this. Why isn't this working? Let's see if I can figure this out. Does it have this?
During DNA
Okay,
replication, both strands of the double helix act as templates for the formation of new DNA molecules.
Of that mechanism is just you have a
Copying
strand of DNA,
occurs at a
it's gotta get
localized
pulled
region
apart, so
called
you
the
have
replication
the
fork,
strands, the
which is a
leading and the
Y-shaped
lagging
structure
strand of
where
DNA,
new DNA
right?
strands are synthesized
And
by a
here's the
multi-enzyme
helix that's
complex.
pulling it apart. Here's DNA polymerase. And look
Here,
how
the DNA
fast
to be
it's
copied
polymerizing
enters the
that
complex
DNA.
from the left.
With a reaction
One new
that
strand
wouldn't
is
normally
leaving at the
occur
top of
at room
frame,
temperature,
and the other new strand
for
is leaving
any
at the
purpose,
bottom.
or at body
The first step
temperatures
in
even.
DNA replication is the
It's just-
separation of the two
it's just
strands by an
unbelievable,
enzyme
right?
called
That
helicase.
it can happen that fast.
This spins the
And that's
incoming
because of
DNA
the
to unravel
amazing
it at
ability
10,000
of your
RPM
enzymes in your
in the
body
case of
to do
bacterial
that,
systems.
to orient molecules, to
The
position them
separated
correctly,
strands are called
and
3'
put them just in the right way, position them in
and
just
5',
the perfect way to do that.
distinguished by the
And it has to do
direction
that
in which their
super good.
component
You can't
nucleotides
just
join
make
up.
mistakes. What's going to happen if it makes mistakes?
The 3' DNA
You get
strand,
mutations,
also known
right?
as the leading strand,
And then
is diverted to a
that's not
DNA
good.
polymerase
You're going to have
and is
genetic
used as a
diseases and
continuous
disorders,
template for the synthesis
um,
of the first daughter
Lou Gehrig's
DNA
disease
helix.
from one single
The other half of the DNA double helix,
DNA
known as the
nucleotide
lagging
that's
strand,
copied
has the
incorrectly.
opposite 3' to 5'
Can cause you to
orientation
have,
and consequently
genetic
requires
disorders
a
like
more
that.
complicated copying mechanism.
And so it has to be super
As it
good
emerges from the
at what it
helicase,
does.
the lagging
it is.
strand is organized
super
into
good.
sections called Okazaki fragments.
Okay. So those are catalysts. That's what they do. Okay. They lower the activation energy. Here's a catalyst for the Haber process for the synthesis of ammonia. Remember, ammonia is a triple bonded molecule. Nitrogen, I'm sorry, not ammonia, but nitrogen. Nitrogen is triple bonded. And, you know, they wanted to be able to make nitrogen or break the bonds of nitrogen to create ammonia back in the day. And they couldn't figure out how until they developed this solid phase catalyst that has these different metals and things associated in it that will bind that nitrogen and everything and increase the stress on the bonds and allow the bonds to come apart. Okay, and then once they do, the molecules can rearrange themselves, and then they will come off as ammonia, as NH3. Okay, now this process was originally developed by Haber, which is a German scientist, because he wanted to make bombs. So World War I, which was no fun. But yeah, that's how it came about. But now it's a very effective process for, you know, creating fertilizer and different things like that. So it's very useful today, even though it was very nasty back in the day for what they used it for. Chemical warfare, not good. Okay, so here's the decomposition of N2O5 into NO2 and O2. Okay, it decomposes into those two products. So this rate of this reaction is proportional to the concentration, because there's only one thing. So if I increase the concentration of that, it will decompose. Okay, and that's how that reaction rate is affected by that. Okay, so how do I mathematically represent the rate of a reaction? So you can determine, and you don't have to calculate this. I keep saying that because you guys are lucky, right? If you were in my Chem 2 class, you'd be doing all the kinds of crazy calculations for this stuff, but you don't have to, okay? So you guys are lucky. All right. So here you're going to just simply be able to recognize the correct equation for the decomposition of a certain reaction or for the combination reaction, whatever it is. Okay? So mathematically, I only have one reactant here. So in my mathematical equation here, I'm just going to have one reactant. That will be represented. Okay? That reactant at that concentration will be multiplied by its rate constant. This is the rate constant. Okay? Right there. Rate constant. Which is little k. All right? And so this rate is going to be equal to or based on the rate constant and the concentration of the reactant or reactants. Okay? So here we see it written a little differently. If A decomposes into these products, then the rate is equal to the rate constant times the concentration of A raised to N. So what does N represent? It represents the order of the reactant. And we'll discuss that next time. Okay? So we'll see you guys.